Thank you very much for the introduction, Glenn, and good morning to everyone. Today, I would like to talk about thermal testing of semiconductor components. Some of you may have attended my presentation last year at the face-to-face TFAWS event, where I talked about silicon carbide components, and I think for many people, I just jumped in the middle of things and didn't really talk about the basics. So this is what I would like to do this year. So here are the topics of my presentation for today. I will give an introduction to thermal transient testing and focus on what we call the structure functions, which beside giving you thermal data of semiconductors, also gives structural data, understanding why the temperatures may stay hot or why it may be difficult to cool down a given component. In the second section of my talk, I will talk about thermal model calibration, which is basically a correlation technology very similar to what Dr. Hengewald discussed right before me, at least part of the technology he introduced, using test data to make simulation results more accurate. Then also these accurate results can be exported as reduced order models. And finally, I will very briefly talk about power cycling testing as sort of lifetime test, and combining all these technologies, you should be able to predict lifetime of the entire system which we are building, which would be a complex system, for example, the previous Mars helicopter, which we've just seen. And at the end, there will be some time for questions. The reason I was thinking of giving this talk today is the ever-increasing electrification in the aerospace industry. We've seen this in the automotive space for quite a long time. You can see hybrid cars already for more than 10 years, and more pure electric cars are being introduced. And the same thing is happening in the aerospace market as well. And not only small airplanes are being developed, but flying taxis, passenger airplanes with 20 or even higher number of seats. And as the engines of these aircrafts are electrically driven, the reliability of the engines and other electronics components is extremely important. So when it comes to thermal testing and temperature induced challenges, many of you may have seen the pie chart on the top left corner of my slide, which was done by the US Air Force many years ago. And they were kind of interested what factors led to failures of electronic components, and especially the battlefield application. And 55% of the time it was temperature. And the second most important contributor was vibration and then humidity. And the problem with temperature when we design cooling solutions, as actually you could see in the previous presentation, in the aerospace industry and even in automotive, there is actually smaller and narrower design margin thermal engineers can use. The power is increasing both on the power electronics side and also on the logic side. But systems have to be lighter, they have to be smaller. So we cannot just use rule of thumb design rules, which were pretty common 10, 15 years ago. And again, the reason this is important, temperature influences reliability, but also in some cases, it influences performance, especially for LEDs, LED-based light sources. And I'm talking about high power, such as headlights, indication lights, or also for complex ICs. If you can't keep an IC cool enough, it may either fail, or you may need to do what's called frequency throttling. You need to go down with the clock frequencies, making the system less efficient. And I've already talked about system margins, for example, system costs, and most importantly, weight has to be reduced. So traditionally, in order to understand temperatures, we use thermocouples and IR cameras, which are actually easy to use and excellent tools. The only issue is when we would like to characterize a semiconductor component. These tools don't have access to the most important part of the component, which is the junction temperature of the semiconductor. Typically, you can use these to measure case temperatures. Or if you want to get closer to the junction, you need to decap the component, which changes the thermal field and makes the measurement unrealistic. So instead of this, what we recommend doing for semiconductor components is so-called electrical test method. It's actually a standard methodology. You can find descriptions in the JEDEC GSD 51-1 document, the US military standard 750D document. Basically what it does, if you take a look at this IGBT here, we can measure its temperature by providing a constant bias, like we call it a sensing current across the component by opening up the gate, so putting the device into saturation mode. And the device at a steady bias will change its output voltage, collector emitter voltage in this case, as the temperature changes. Actually, this chart here is it corresponds to a single silicon diode. And what you can see is if the device temperature goes up, then at constant bias, the device voltage will go down. This is something you can calibrate in a thermostated environment. So practically every single semiconductor component you may use in your application can be transferred to a built-in or a temperature sensor. And then once you know this relationship between temperature and voltage, you just need to create a voltage step, temperature step, measure the voltage change, understand what the temperature change will be. Let me show you this. So you take a semiconductor component, it can be anything. The first step you want to do is to determine the semiconductor component's temperature sensitive parameter, which for a diode is the forward voltage at a constant sensor current, or for an IGBT, it can be a collector emitter voltage, it can be a threshold voltage of a MOSFET. There are a lot of options for different type of semiconductor components. The next step is to calibrate your component. Typically, you don't really find this data in a data sheet. So what you need to do is provide a biasing, place the component in a thermostated environment, change the temperature externally, and measure the component voltage as it changes with the change of the temperature. That gives you a calibration factor. And once you're done with this, you are ready to do the characterization. And typically we start with the power step, change the power sharply, and measure the corresponding temperature response. You'll see in the next slide that this is basically used as a probing function to understand not only the temperature inside the component, but again also to understand what the structure of the component may be. What we try to come up with at the end of this characterization process is an RC, thermal resistance, thermal capacitance network model of the component, starting from semiconductor junction, which is the origin in this chart. And we actually plot how this RC field develops as the heat wave propagates from the heated die all the way through the components or the different layers of the component. You see a cross section of an IGBT on the right part of my slide. So there is your die, there is an attachment layer called the die attach, and there is a DBC substrate, copper, solder, insulation, copper frame on the other side. And using structure functions, you can actually determine the corresponding thermal resistance values, the corresponding thermal capacitance values, each of these layers. And I will show you in a moment why this is important for you. So before I get there, how do we do this? You've seen how the temperature is measured. And once we had that temperature calibration, we did a power step. The reason we do a power step, if you have a system with, let's say, a known weight function, if you have any type of input power function and you convolve it with the weight function, you should be able to analytically calculate the temperature response of that component, no matter how complicated that input power function would be. In our case, we don't have that weight function ready. We have an unknown component. So we take a unit power step as an input, well-known input, and we measure its response, the unit power step response function. And if we inverse the convolution, so we do a function called the deconvolution, we can actually analytically calculate the weight function of the system. We can understand what the system is in terms of thermal R's and C's, which gives a certain output for a given power step input. Why is this important, or why is this potentially giving you more information than just looking at the temperature response? I like to demonstrate it with a very simple simulation experiment. Let's take a copper rod. You heat it up on one side, and this plane on the other side, it represents an isothermal surface like a liquid cold plate. And we've done two simulations. One was just a copper rod, 100 millimeter long. The other one was same copper rod, but in the middle, 20 millimeter section was simulated with a double thermal capacity material. And if you do the analysis in the time domain, you see that you get pretty similar responses. Of course, if you have higher thermal capacitance, then the time to get to steady state is slightly longer, but with these boundary condition changes, it's not even very significant. If you transform this into structure functions, so a thermal resistance, thermal capacitance model of your structure, the changes become very significant. So initially we had unit resistance, unit capacitance. So basically in both cases, the same structure function is obtained. They are overlapping, and there is a certain ratio between R and C. And once we get to the point where the changes were made, we have double the capacitance for unit resistance. So we've just changed the ratio 2:1. This way, the slope of the structure function will also change 2:1. So you see a big change, big difference in thermal response here. Things get a bit more clear. And once the heat gets back to the original copper session, then basically the two curves, they again come parallel to each other. So the message here is that using both time domain and structure function analysis, with the help of the structure functions, you can see changes way more clearly, even though they are small. And what they physically mean, this simulation here represents a simple TFAWS2020 power transistor. You can see the base of the component here. You can see the leads right here. And what's covered by red, that's the die. And over here, there is an overmold, which is basically the top of the package. Heat doesn't really go that way. And if we do a simulation, like a steady state simulation, you can find regions which are covered by isotherms, like we have the whole die here, named by 1. Number 2 is the base plate. Number 3 is the near environment, and number 4 is the cold plate environment. So what we can do, we can get the RC values analytically out of the measurement for each of these regions. And the physical representation is, for example, for the dye, the distance or the difference of the temperature between the highest temperature point and the isotherm covering the dye over the power dissipating through this surface will give you all these thermal resistances. The volume which this isotherm embraces times the specific heat of the material will give you the corresponding thermal capacitance. So you can get real thermal resistances from one layer to another, and you can get the spreading thermal capacitances. As you can see, number 2 doesn't fully align with the package base, but this is basically where the heat is going. So some of the applications you can use this to measure package characteristics, like changing a boundary condition right after the package. Structure functions will also change, and the common area, the common part of the structure functions which show the heat still just going through the package, arriving at the package base, they can give you data such as the junction to case thermal resistance. So you can either obtain or verify datasheet metrics for components. I will show you this in details. You can do multiple structure function analysis while you are doing some reliability or lifetime test. The change of the structure functions will indicate changes or failures within the component. I will discuss this one in detail. You can use it for quality testing. So when you manufacture a component, or let's say in an aerospace application, when you select components which you build into system, you launch into orbit or farther, you can't retrieve it. You want to make sure that not only the component meets the datasheet values, also it's fault-free. So let's say in the die attach layer between the semiconductor and the package, there are no voids, no delaminations. You can check that the component will fit its purpose. And you can also use the technology for model correlation, which I'll show you in a moment. So briefly talking about model correlation, this is an IGBT with 2 IGBT components, the half bridge in a dual side cooled package. And this is a CFD model we created describing the physical package as well. How can you use this technology for correlation? Actually, there are 2 ways. One way is not even correlation. For one deep heat spreading case, you can actually take the package, make a measurement, create a structure function. That structure function is essentially a one-dimensional RC network model. So you can export it into a simulation tool and use it directly for a quick thermal simulation. If, like mostly in this case, or in case of a digital IC, the heat spreading is more 2 or 3 dimensional, then you can still make a measurement, create a structure function, store it, and you can actually recreate the physical conditions in your CFD space. And you can analytically create a structure function based on the CFD simulation as well. And then you can compare the two, the test and the simulation-based structure functions. And the difference between the two will highlight where there might be inaccuracies in your model and how you want to change them. And once your model is already calibrated, you can take a very similar approach, which we heard earlier. For example, you can create a raw model for much faster simulations. In our case, this package had 2 heat flow directions. Even though, as you could see, the structure functions are primarily a one-dimensional model, you can still use it for a 2-dimensional case because their sensitivity to small changes still remains. So what you see in this slide for the 2 IGBTs which are in the package, we measured 2 different transient responses. see time on the horizontal scale and temperature on the vertical scale. And on the right side, you see an equivalent simulation showing you the heat flux vectors going both up and down. And ultimately, as the device was not cooled on the top side, turning back a little bit in steady state and going also downwards. And what you see here, these are the structure functions. The measured structure function is shown in blue, and the base structure function, which we created on using the uncalibrated model, is shown in orange. And as you see, the shape is similar, but the resistances are slightly lower. This is because typically it's very hard to know the interfacial thermal resistances between material layers. So we didn't have that. And we had to implement those in the simulation and had the tool. We used Flowterm for this simulation. We had the tool figure out what those values were. After optimization, the optimized simulation model is shown in green. The green and the blue curves, they overlap very well. So typically, if you don't do this, you may miss some of the resistances and you might underestimate your thermal resistances in a system. A few slides on lifetime testing. One of the typical lifetime tests for power semiconductor devices is active power cycling, where you electrically turn on and turn off the component in a cyclical way, and I'm sorry, and try to break it. So typically, in order to understand what happens to your component, you need to stop the process, take the component off the test bench, do some sort of analysis, typically X-ray or ultrasonic microscopy, to understand if there is any voiding developing between the semiconductor component and the package. And once you have that information, just put the package back to the test and continue. This is a very, very tough process, and actually you may lose some of the information as you have no real feedback what's going on with your package. So we had an idea to kind of combine this workflow with thermal testing. And before I show that, I'm just showing a simulation model, what happens when you turn the heat on and off. Basically, the colorful areas are temperature gradients, and in key areas such as the die attach or the base plate solder, we have very high temperature gradients leading to high thermal stress. And that can break the die attach layer. So what you see here, we took an IGBT, cycled it, and the cycle numbers are shown in the chart from 0 to 35,000. And as you can observe, up to like 15,000 cycles, the structure functions didn't change. But at around 20,000 cycles, you see a slight change right here at the die attach, showing that the thermal resistance of the die attach is increasing a little bit. And that indicates a failure in the component. If you keep on cycling, this region here gets longer and longer and longer, which actually shows, I'm sorry, an increasing die attach void, which is basically leading to the ultimate failure of the component. So you can understand what's happening, at which cycle number, and you can either select a different component or change your design. And my last slide, this can be used to understand how many cycles of operation you can expect at a certain junction temperature. You can measure both the cycle number to failure and the junction temperatures very accurately. And you can use those correlated simulation models I showed earlier to, after this, simulate your full system's thermal behavior, combine the two information in order to give you a very good estimate how long your system or subsystem would operate in certain temperature or load conditions. So just to summarize this very quickly before I run out of time, the best way of measuring a semiconductor component, any semiconductor component, is use its own electrical parameters to measure its junction temperature. And if you use this structure function methodology I showed you, you can get an understanding of the thermal behavior of the component, its external cooling solutions, and you can combine it with CFD simulations to get an ultimate, very accurate 3D CFD model of your package and the entire cooling environment to get you like vision profile based lifetime estimate at the end of the day. So thank you for listening, and I'm very happy to take questions.
You can submit your questions in the chat box to the right of the stream.
I see we got one. What type of electronics components parts can be characterized using thermal transient test methods? So Peter, thank you very much for this question. Basically, the reason I wanted to show this presentation today, this methodology is very useful for inverters used in electrical traction, so motor drives, motor controls, energy conversion between a battery and an electrical engine. But this is not the only application. You can use it for LEDs or lasers, laser diodes. And you can also use this for more complex ICs. Actually, it's kind of surprisingly simple how an SoC or a multi-core IC component can be tested using this methodology. And those components can be very important for optical processing, digital processing, or sort of subsystem control. There is another question from Jerry. Thank you for that. Is this process used to measure interfacial resistance and component effective resistance? So what we do is, from the junction perspective, we capture the thermal resistance from semiconductor junction to the ambient, and that includes everything. It includes the like junction to case thermal resistance of a component. It includes the partial thermal resistance values of the different features, and also the interfacial thermal resistances among them, plus the external cooling solution too. Now, you can easily see the partial thermal resistances of major parts from the structure function directly. But if you're interested in interfacial thermal resistances, it's always best to use a combination of test and simulation. And very similarly to what I've shown with the dual side cooled component, you can use simulation to exactly get what the interfacial thermal resistances will be from component or layer to layer.